Hi, so this is a video editorial for the LeetCode weekly contest 498. This contest was the difficulty was on the easier side, I'd say. Q1 to Q3 were relatively straightforward, and Q4 had a decent idea. But like, if you have some knowledge with, let's say, I'll spoil it with digit DP, then this is fairly easy to solve as well. So I'll be going through my solutions which I implemented during the contest in the order of the problems, and after my explanations of the solutions, I'll be attaching a live solve section where you can see me how I approach these problems in a live contest scenario. So Q1 and Q2 were the same problem but just with different constraints. Q1 had n less than equal to 100, and Q2 had n is the length of the array, less than equal to 25. So my idea for Q1 was the problem Q1 is basically like given an array, its instability score is defined as the max of its prefix. The instability score of an index is defined as the max of a prefix minus min of its suffix elements, right? And the index I stable if this max minus min score is less than equal to k, and we have to find the first smallest index which satisfies this. Now obviously you could run a brute force solution for this for part 1 at least, where at some index I you find when you are checking for some index I, you run a loop from 0 to I to check the prefix score, and then run a loop from I to n minus 1 to check its suffix score and then calculate it. This will work for n less than equal to 100, but I wanted to solve part 2 at the same time as well, and for part 2 we had n less than equal to 25. Now for this the idea is still straightforward. The prefix max we can maintain while we are iterating, right? Pfx can be just max of the current pfx, comma the the current element, which is num psi. This would be the current pfx. Now at some index I, what we want is to know the current suffix min as well. So what we can do is we can pre-compute all of the suffix mins for a given input, and then run a loop. While running the loop, maintain the prefix max, and then check if the suffix min and prefix max score satisfies the condition. So my solution for Q1 and Q2 is exactly the same. So I'll just go through my Q2 code since I just copy pasted my Q1 code into this and it ran. So basically we make a suffix min. This is suffix min array. Initialize the last element to infinity, which is, I chose mod as infinity because max value here is this 1e9. So we mod is 1e9/7. What happened? Yeah, so we create this, and for every index I, we first compute the prefix max. We compute the score. If score is less than equal to k, that means this is our first index which satisfies it. So we return I, else at the end we return -1. So this was Q1 and Q2, fairly straightforward. Q3 was like Q3 was a straightforward problem as well. Basically, we are given a sources I, which contains the, first of all we are given a matrix of n cross m, where n is the rows and m are the columns. Columns, rows and columns, and we are given a sources array which contains I comma j comma color. Now I comma j is the starting point, and from the starting point we have to spread this color, and we have to spread the color with the following rules. All of the currently colored cells spill simultaneously into its directions, into its neighboring directions, which are up, down, left, right, and all of the spreads happen simultaneously. If multiple colors reach the same uncolored cell at the same time, we try to choose the one with the maximum color. So yeah, this is like straightforward. If you remove this is just a multi-source PFS problem, but this part we have to ensure that this part remains consistent. If multiple colors reach the same cell at the same time, then we have to ensure that we are keeping the one with the highest color, and this continues until no more cells can be colored. So yeah, if you have some experience with BFS, this is like a straightforward implementation of a multi-source BFS, which is where we start BFS from multiple cells. Let's say we start from these cells at once. So this will spread like this, then this will spread like this, then this will spread like this, and now from these cells this will spread like this similarly. Now the interesting part, the main part for this problem is ensuring how we handle the case where two cells, let's say this cell and this cell, reach this part at the same time. Here we want to maximize the spread from the larger color cell, right? So there are two ideas here. first idea is, instead of a queue, you could have used a priority queue where we push the color, comma the cells. Now since we are, it's a max priority queue. So here what would happen is, since we are pushing a color as the primary key and then we have the index, and since this is a max priority queue based on color, this will automatically prioritize the colors. This will automatically prioritize the larger colors first, so they will do their fills, and then for the smaller colors we'll see if it's already visited, then we don't visit it. So this was one idea, but I didn't do it like this. For the BFS part, I used a normal queue. Normal queue, and then I was doing it like this. Like my BFS implementation was going layer by layer. First of all, I am spreading cells like this, and like this. Like I'll first see which current cells I have to visit in this layer. Layer is the basically, if we do a BFS on a tree, it would, like for an example, if we do a BFS on a tree, going layer by layer is like going like this, like the visiting all nodes at the same height. Here the height would be the distance from the source. So for this layer, I am noting the size of the current to visit, and I am only iterating on these. And this is straightforward BFS idea where we get the node to visit and its color. Now this thing, basically, if the color which we are trying to color this cell with is less than the color which has already been there, that means that a higher color, a larger color value has colored this cell, right? And we want to prioritize larger values. So in this case, I'll continue. Else I'll do this, the regular BFS thing, where I've created the direction array. If the next index is inside, if the cell we are trying to visit is not visited at all, then we can directly visit it, right? So here I'm marking that with the current color. I'm pushing this, and this cur, I'll explain what it is. Cur is basically the nodes which I have visited in this layer. In this basically, I explained this layer, right? In this layer, what are the cells I have visited? So and since I'll visit this cell now, I'll put this in inserted. Now if this, we have visited this, but we have visited this in this iteration, and the color there is less than C, which means that we can maximize its color, right? Since this says if we are visiting it simultaneously and we can maximize the color, then we prioritize the larger color. So in that case, I'll update the color and I'll push this, and this check ensures that I'm only processing the larger color values first, and at the end I just return the color array. This implementation is a bit like unconventional, especially when compared to the priority queue one, but I was doing like in the context, this felt more natural to me, so that's why I implemented this like this. So this was Q3. Q4 was a nice problem. Basically, we are given two integers, L to R, and its string directions, which is exactly of length 6 and contains exactly 3 Ds and 3 Rs. Why is this important? I'll let you know. First, what we have to do is, for some integer x which is inside this range, first, if the number of digits is less than equal to 16, we have to pad it by leading 0. So let's say I made this example. Let's say we have this number 12406 37010. This currently has 10 digits, right? But 10 is less than 16, so we have to pad it by 6 leading zeros. Now this will have exactly, I'll do zero-based indexing here. Now this has exactly 16 digits. Now for this, we have to divide it into a 4x4 grid in a row-wise order. So the 4x4 grid here would be 0, 0, 0, 0. We split it here, 0, 0, 1, 2. We split it here. Then we have 0, 6, 3, 7. We split. I might have made a mistake. 0, 0, 0, 0. Yeah, I made a mistake. 1 second. 0, 0, 0, 0. Split it here. 0, 0, 1, 2. Then we split it here. 4, 0, 6, 3. And then we split it here, 7 0 1 0. Now this is our 4x4 grid. I'll index the rows and columns in zero-based again. This is our 4x4 grid. Now what we need to do is we need to follow the instructions which are followed in the direction string. So let's say we have RDD RDR. Let's say we have this RDD RDR, which means this is our direction of iteration here. Right, down, down, right, down, right. Now this will give us a number, right? Wait, this is 6 by the way. This will doing this iteration on this grid will give us a number, and the number we will obtain here is 0. 1 second, 0 0 0 6 1 0. Now if this number, the digits are strictly non-decreasing, then this number is good. And if this obtained number from the digit is good, if the this iteration, if this number is good, then that would mean our initial number was good as well, which we obtained by splitting it into this grid, right? And this good, we have to count such good numbers in this range. So this explanation for the problem was kind of long, but it is important to understand the exact what we have to do in this problem. Now, as I stated, we have to count something in the range L2R, and the L2R values are fairly large. Yeah, this is, I just assume 1E16. They gave 9 into 10 power 15 because they want 16 digits, right? But I just assume 1E16 to be my max thing. So basically, obviously, count in a large value for some conditions. So I was like, okay, digit DP. So, and which intuition was correct. Now the thing is, how do we check this? Ensure that this thing is, is good. Because obviously we can't actually form this, right? Because this number is fairly large. This is 1 2 3 4 5 6 7. This is 7 digits, which would be like, let's say it can fit in 10 power 6 or something. 7 digits would be like 9 9 9 9 9 9, right? We can't keep this in the state since this is like basically 10 power 6 only, 10 power 10 or something. We can't keep this in the state. So my idea was, in my implementation, what I did was, these indices are all representing a index in this flattened array, right? So what I did was, I first of all noted which of the flat indices are important. So here the important indices are these 0, 0, 0, 1, 1, 0, 2, 0, 2, 1, and this is, what is this? 3, 1 second, 0, 0, 0, 1, 1, 0, 2, 0, 2, 1, and this is not 2, wait, what? My bad, this is 0, 0, 0, 1, 1, 1, this is 2, 1, and then we have 2, 2, then we have 3, 2, and then we have 3, 3. And their flat indices would be 0, this would be 1, this would be 4 plus 1, 5, this would be 8 plus 1, 9, this would be 9 plus, this is 8 plus 2, 10, this would be same plus 4, 14, and then this would be 15. These are our important indices. And at these important indices, we can just do the digit DP. Like for these important indices, assume we are solving the problem where we are counting the number of digits which are such that they are non-decreasing, right? And so for the non-decreasing thing, we can use a previous in our digit DP state, which is the previous digit, and just track if it is less than equal to the current digit, right? And since we have this important indices pre-computed, we'll just do our digit DP, and only for the important indices we'll handle the previous condition. So this was my implementation. First of all, this I've created this thing for the important digits, and if this is basically me noting down which digit is important and not, and the 0th, which is 0, 0 is always important because we'll start from there. Once this is done, then I'm just doing the digit DP solve where I do for r in L-1 and then I subtract and get the answer. Now for the digit DP solve, this is me just padding so that the length is exactly 16. Then my DP is basically obviously tight and started. Started is not necessary here, but I have learned to keep the state so that it just makes debugging easier. The previous digit, and this previous digit is actually not the previous exactly the previous digit. It's a previous digit which was placed at an important index. So I'll show you this. First of all, this is a generic the upper bound set for digit dp and the current res. Now if let's say the digit is not important, then we'll just this is the next write, this is the next started, this is the here the since the current digit was not important, we won't update previous write since we want previous to be just the previous important digit. So in this case, previous is equal to next previous is equal to previous, and ni is obviously I plus 1, and then we just do the digit dp transition. And if the current index is important, then the currently placed digit should be greater than the previous important digit, right? So let's say here we are trying to place this, which is 1 comma 1, which would be 5. So here we are trying to place something at 5. So this should be this should be greater than the previous important digit, which was 0 comma 1, which was 1. So since we already have this in our prev, we here try to ensure that d is greater than equal to prev, so that our non-decreasing condition stays holds true, and then we can just do the same transition. But here we will also update and the next prev to be the current digit, right? Since for the next important digit, which is 9, it should look at this, right? So yeah, and then we just do the digit dp transition. So this was my implementation for Q4. Q4 was a fun problem, but yeah, outside of that, Q1 to Q3 was really straightforward. Alright, if you have any doubts in my explanations or any issues or something, or clarifications which are required, let me know in the comments. And after this, I'll attach a live solve section where you can see how I approach these problems in a live contest scenario. Alright, bye.